general stuff about your exam that's coming up. There is a place to put questions in the chat, and so what's going to happen is somewhere between 20 to 30 minutes, I'll definitely stop and ask for questions, and the fantastic moderators will also interrupt me. So I'll also be just pausing at various intervals for those too. So we definitely will take questions live. We also took questions via the registration link, so I have some of those already all queued up, but because it's the very first exam review, and therefore your very first exam that's coming up, we're going to cover some general things that you may or may not already know, but that way we're all on the same page. So first of all, it is at 10 a.m. So for those of you who took Gen Chem 1 with us last fall, you may remember that essentially what we do is we have a time window for you to begin your exam in, because we understand that sometimes you sit down, you open your computer or your laptop especially, and you realize that your charger for your laptop is like on the other side of the house because either your roommate or your sibling borrowed it, so you have to go run and go grab that. So we do give you a window, but this window is only 30 minutes. So you need to plan on getting into the exam between 10 a.m. and 10:15, because that way you don't run up against that 10:30, because we will basically close that exam window and you won't be able to get in after that. So do plan on sitting down like at 10 till, 5 till, getting yourself all nice and situated, and actually hitting go at 10. And then that way, if you have to go find your laptop charger, you've got time to do that. The date is in fact Saturday. So we are now at that less than a week time. So that is Saturday, February. Why do I suddenly now not have what day of the week it is? Anyway, I suddenly don't remember what day. Oh, it is the 12th. So it's like I thought it was the 12th, but suddenly my brain is not remembering how weeks work. Saturday, February 12th. It is all online. So remember that your midterm exams, which we technically classify this one coming up as a midterm exam, these are all online. Quick reminder that your final exam is in person. So this will be different from what we did last go around. The other thing that y'all should have been working on over this weekend is you will actually need Lockdown Browser. So there is information, which I'll show you in a moment, on how to access that, but you will need Lockdown Browser to do your online exam, because we are expecting this to be closed book, closed note. So you will need Lockdown Browser for your exam. This is going to cover chapter 13 and most of chapter 14. So we basically got rid of the last 3 sections. I am going to hop over and show you the announcement. So in our course, there's usually a course where you have your regular lectures, and then there's also a course called the 7W1 section. So in 7W1, we have a plethora of announcements because this has been a very active and interesting semester already. But basically, we are going to cover chapter 14, 14.1, 14.2, 14.3, 14.4, and 14.5. And then leave the rest of the chapter, which is going to be, so not 14.6, 14.7, or 14.8. These we are just going to save for exam 2. So we will still cover these, but 14.6, 14.7, and 14.8 will be on exam 2, not on exam 1. So we will still cover them, but we will cover them a little bit later to compensate for the day we lost to the winter weather. So that was all of the stuff. So you will take your exam in the 7W1 section. So that is also where your practice quiz is located. There's also where your Lockdown Browser instructions are located. It's also where the recording for this exam review, by the way, will be, because there's an entire folder dedicated to exam reviews. And this is where all the information, including the notes that I write down, as well as the recording information, will go as soon as I have it. Also, if you haven't actually ever logged into this part of e-learning, this is also where there's pre-recorded content that we actually made last spring. But for those of you that are like, oh no, I got so used to everything being recorded, now we're going back to in person, there is actually information on everything that has been pre-recorded, and it's all hanging out in the 7W1 section because we put a lot of stuff in there. Are there any questions so far?
There is this one question which asks, given that the exam requires lockdown browser, will we still need to use the webcam feature?
No, you do not need to use the webcam feature. So lockdown browser, if you watched any of the promotional material, everything I ever saw on it had this, so I understand this question because it usually is like, if you're using lockdown browser, you're probably also using. We're not. So there's another thing called Respondus Monitor, and that is something that the university does not already have a license for, and we were given the fascinating choice of either having the chemistry department pay for that or passing that fee on to you, and we've done neither. So lockdown browser, the university already owns, the university already pays for, so we are using the thing that's free. But that lockdown browser does not require a webcam. So good question though, very good question. I have already gotten that one a couple times because if you read, watch anything about lockdown browser, you can't avoid Respondus Monitor, but we are not using Respondus Monitor, but we are using lockdown browser. So I totally understand. They're usually used together. We are not. We are using only one of them. Anything else right now?
I think we're good for now.
Okay, fantastic. So then I'm going to go ahead and move on to some of the questions that y'all sent in. So we got things like identifying polar and non-polar molecules. So I am going to go ahead and cover this and just kind of talk through this. So a couple of reminders with polar and non-polar molecules. So this is something that we actually talked about way back in chapter 7. So a lot of Gen Chem 2 is cumulative back to stuff that we did before. So while I will go ahead and talk about this, if you're like, I could use some more of that, or I could use more practice, your practice is actually hanging out back in chapter 7. So essentially, what we talked about when we did polar and non-polar molecules is we would often have things, we'll just go ahead and start with the model we use a whole lot, which is water. And there was a time, which was actually back in chapter 6, where you would go ahead and draw the Lewis structure for water. So in drawing the Lewis structure for this, you would do things like identify the valence electrons. So you would grab the periodic table, which will be at the top of your exam, and you would find that hydrogen here has 1 valence electron, oxygen here has 6 valence electrons. And so when we're coming back to think this through, I have then 2 hydrogens, so that's 2 valence electrons plus 6 from the oxygen, which is 8 valence electrons. You'd go ahead and put your oxygen in the middle because your hydrogens can only form a single bond. That's one of those unique parts of hydrogen. And so I've already used 2 bonds, so that's 4 valence electrons, gives me 4 left over. Those are going to go as lone pairs. Now, here comes the part which was more, so this was a chapter 6. So in chapter 6, we drew Lewis structures. This is a chapter 6 Lewis structure. In chapter 7, we went ahead and looked at the fact that while this is fine for a Lewis structure, because Lewis structures focus on valence electrons, what atoms are bonded to which atoms, and how does all of that work, this is not actually a good shape for this molecule. And the shape does actually matter. So in chapter 7, we started to talk about the fact that this is actually in 2 dimensions, and in reality, we live in 3 dimensions, and so do molecules. So in reality, this is the water molecule where you should have essentially on one side of it 2 lone pairs, and on the other side, your hydrogens. So essentially, you have all of this negative stuff because you have all of these electrons that are not being shared, they're just sitting in one location. And since they are sitting in essentially trapped on the atom, you're going to get more negative stuff on one side than on the other. So those tend to be more negative, these tend to be more positive. So this then is where we can finally start to talk about this idea of identifying polarity. So when the goal is to identify polarity, I summarize about a chapter and a half worth of information because that's all stuff left over from Gen Chem 1. So we'll talk through some of the shortcuts that we can potentially use too. So as far as polarity then goes, really what we're looking for is this idea that the electrons are not evenly distributed. Lone pairs on a central atom are usually a good indicator that you have a polar molecule, that you've got more negative stuff on one side than on the other. So because essentially if we had a second water molecule, you would expect opposites to attract, and therefore the partial negative of the water molecule to be trying to hang around the partial positive end of the water molecule. So this idea is what we call a polar molecule, where you have an uneven distribution of electron density around a molecule, and that's going to cause a natural attraction in between them. So that's polarity. So you would say that those molecules are polar. Now, to do a little bit of emphasis on remembering things from last time, one of the shortcuts for nonpolar that we talked about back in Gen Chem 1 is that anything that involves just carbon and hydrogen is automatically nonpolar. Now, this did also go back into electronegativity and the fact that a carbon-hydrogen bond is not very electronegative. It's pretty evenly shared in between those two. And the other bottom line is when you interact with the world around you, we use water because so much of the planet is made out of water. And as human beings, we interact with water a lot. So essentially, if something interacts well with water, we're like, cool, polar. And when things do not interact well with water, good chance that's therefore nonpolar. Things that are made of just carbon and hydrogen do not interact very well with water. So whenever you have either gotten like butter or olive oil on your hands, just plain water won't do. You usually need something like soap to actually help get all of that off. That's because of that nonpolar nature. So carbons and hydrogens, and that's all you have. Doesn't matter how many of them you have. If that's all you've got, you don't actually even need to draw it out. If that's the only information you have, those are nonpolar automatically. The times where you have to watch out then are those times where you may have something like this, which this one, I can go ahead and draw it out, but essentially you have this oxygen here. Oxygen's very electronegative. So because of that oxygen, I realized that, yeah, the carbon would be nonpolar. The oxygen, though, is going to make the molecule overall at least a little bit polar. So I'll go ahead and draw this just for fun. So there's my carbon and my 3 hydrogens, my oxygen with its lone pairs and the hydrogen off of it. So this molecule would still be polar. So I understand that there's always more. Again, we spent a chapter or two on investigating both Lewis structures as well as polarity. And so you may have noticed that it usually takes a week to 2 to 3 weeks to go over information in that amount of detail and depth. So the fact that I tried to do a crash course in it in 10 minutes, probably not enough. So in general, when you're trying to refresh on some of these topics, some of the options that you have are your book does in fact have information on all of it. So it's part of the reason why we have a required textbook. Also, polar and nonpolar is something that things like AP chemistry cover. So if you're looking for polar and nonpolar, those are also something that you can find YouTube videos on relatively readily, because that is a topic that comes out of high school chemistry. So I know that it's a lot, but this Gen Chem 2 is a relatively cumulative course back to Gen Chem 1. So there are just times where you have to go back and refresh on things like that, because this is not the only kind of molecules that can be nonpolar. I just used the easiest example. To give you another example, just to remind you that shape matters, we often talk about things like carbon dioxide. This is a beautiful example of a nonpolar molecule, because when we do the Lewis structure out for this, this is actually what we would term a linear molecule. And even though my oxygens are electronegative, I have 2 oxygens that pull in exactly opposite directions, and they cancel, the dipole moment cancels each other out. So this actually is what we would refer to as a nonpolar molecule. So again, I know that that's fast. And that really is because it's summarizing about 3 weeks worth of information from last semester. So we could spend the whole 2 hours on that. Other questions on that?
There are a few questions. There's this one question which talks about the constants, and so if there are constants in the formula like PV is equal to nRT, would the constant R and other constants from the other formulas be given with the periodic table, or are we required to memorize the constants?
Okay. Excellent question. I apologize, I forgot to cover that. So the things that we give you. So we are going to give you a periodic table. This periodic table is going to be the exact same one out of your textbook. It is the same one that's hanging out in the practice quiz. It is the one that actually I flipped over to here earlier. So this is just the one, that is the one from your textbook. We pull this one exactly. Actually, it's probably me who's going to add it. This is the JPEG file I have. So it's going to be this JPEG file because it's probably me that does it. Might be Dr. Diekman. I believe he still uses this JPEG file because it's already loaded into e-learning. So this periodic table with these colors, with this schematic, with this number of sig figs, all of that jazz. This periodic table. The other thing we will give you that if you're new to us this semester, we also give you something that we call potentially useful information. And this is the thing that we need to post to that 7W1 section so that you're familiar with it. But essentially what this is this is going to be a list of constants. And what often happens with this is we just add more stuff to it as the semester goes on. So we go ahead and start with the stuff we used back in Gen Chem 1. So you're going to see things like Avogadro's number on here, that 6.022 times 10 to the 23rd. So you're going to see constants on there that we used back in Gen Chem 1 that you may or may not need for the exam. That's why it's called potentially useful information, is because really over time we just add more things onto it. I'm pretty sure it still has things like inches to feet on it. And y'all might not have actually needed that last semester either. We just never have taken it off. So it's there. So constants we will give you. The thing that then you will need to bring to the table. So then the stuff that you will need to memorize yourself is you will need to have memorized formulas. So formulas are things that will not be given to you. The other things that will depend on who writes the question. If you did not already know that the density of pure water is 1 gram per 1 milliliter, now you do. That's information that we usually assume that y'all pick up sometime in either middle school or high school and just have as common knowledge. So that's one of those that if they either didn't cover it or if you don't remember, the density of pure water being 1 gram per 1 milliliter is something we think you know because it's just one. So we do usually assume that y'all know that one. Similarly, the other piece of information that we might give you, but it's such common information to us that we assume you already know it, is we actually assume that you know the boiling point of water is 100 degrees Celsius. This is, of course, assuming 1 atmosphere of pressure, and that the freezing point of water is 0 degrees Celsius. So this is the other thing that we assume that y'all just know because they're nice round numbers. It's how the metric system works, and it's just kind of general background information. We also think you know metric conversions, FYI. So we think that y'all know that there's 1,000 grams in a kilogram, that there's 1,000 milliliters in a liter. We think y'all know that too. So if metric conversions are also something that you don't have memorized, we won't give you metric conversions because we assume that by now y'all know those. Also, if you've gotten away with not having those memorized, I'm sorry, because they're super useful to know off the top of your head, especially if you're going to take science classes. So metric conversion is also something that we assume that y'all already know.
There is this one more question that asks, how do we use density as a conversion factor to get molality or molarity?
Cool. I have examples of that. Dun, dun, dun. So since I brought up density, I've got some other questions and we'll come back to these. But somebody asked specifically from those questions we took earlier, one question in particular, and it also wanted information about how do you know when to use 100 grams of solution or a liter of solution when it's not exactly stated. So I'm going to pull this down here so that I can go ahead and work with this. I'm going to make this a little bit larger. There we go. So rubbing alcohol is a mixture of isopropyl alcohol, and the formula is given, and water. That is 70% isopropyl alcohol by mass, and it gives a density. Express the concentration of rubbing alcohol in molarity and molality. So the other reason was like, aha, the person has asked for molarity and molality, and shockable shocks, I came prepared with both of those. So there is this strange thing where when we're talking about things like this percent by mass is a concentration unit. As a concentration unit, it technically does not matter if I'm talking about the grape flavored drink in my glass, where I have this much of it, or if I had this exact same solution, but I was having a whole bunch of friends over and I had this in like a giant pitcher. The concentration, the amount of stuff per liquid is the same. So I would want it to taste the same. I would want it to look the same. And so by that nature, it doesn't matter if I have this little tiny amount or if I'm planning on giving the same exact flavor wise and look wise of beverage to a group of 100 people or 1,000 people, the amount of liquid would change, but the concentration doesn't. So the weird thing about questions like this, where all I'm doing is going from one concentration to another, is that I get to pick the amount because they didn't tell me how much there is. And so it's kind of up to me. I always pick numbers that are convenient. I think your textbook sometimes does this where the textbook also thinks it picks things that are convenient. Your textbook sometimes does things that I personally would not do, which is it picks the thing that you're headed towards instead of what you start with. Frankly, I always start with whatever you're given in the problem. So this is 70% by mass. 70% by mass means that I basically have 70 grams out of 100 grams. So this is 70 grams would be my isopropyl alcohol. So I'm just going to copy that formula down, H7OH, and out of 100 grams of solution. So this is just taking information out of the problem. I have 70 grams of isopropyl alcohol out of 100. Then I want both molarity and molality. We will do both. We're going to just go ahead and start with A. So since we're starting with A, molarity is in moles per liter. And this is liter of solution. And this is moles of solute. So this is going to be moles of C3H7OH. Whenever you're doing any of these concentration problems, I highly recommend you just take the top part and transfer the top part, and then the bottom part and transfer the bottom part. Also, in case you're curious, I do know the words numerator and denominator, but we won't test you on numerator and denominator. So why would I bother using that terminology all the time when top part and bottom part work just fine? But in case you're curious about my mathematical literacy, I do know what you call the top part of a fraction. So first thing we're going to do is look at going from 70 grams of isopropyl alcohol to moles of isopropyl alcohol. So they gave me a formula. So the first thing I actually need to do is come over and figure out my molar mass using a periodic table. So I can grab all of my atomic masses. So here's my carbon, there's my hydrogen, and here's my oxygen, and I can use that information to calculate the molar mass. So I actually did that one ahead of time. So my molar mass is 60.094. That is grams per 1 mole of my isopropyl alcohol. So what I can do now is go ahead and, again, I'm just worrying about that top part. So this problem, I just copied it from what someone submitted. So when y'all ask me later about significant figures, I just copied this. So I am just going to keep extra significant figures, probably way more than I need. But I'm just going to keep about 5 or so as I go through, because we're not going to worry about the fact that we weren't given that many to start with. I just copied this from what somebody submitted. So there's my 70 grams I start with. I am then going to wind up dividing by my molar mass because I need to get rid of those grams. So that makes those cancel. And I get a grand total of 1.1648 moles. So top part, we got. Then the bottom part. So a couple of things to keep in mind. One is I want to make sure that I'm paying attention to all the bits and pieces. So this is 100 grams of solution, and I'm going to liters of solution. So the nice thing is that I don't need to worry about solute, solvent, any of that jazz. I'm already in the same thing. I'm already talking about all of it. But I do have grams, and I want liters. So I am dealing with going from a mass to a volume. So I am dealing with a completely separate unit. Because of that, then that's where I'm going to use the density. So because I'm getting out of mass, I'm getting out of grams, it's not kilograms, it's not milligrams, all my grams are gone. All of my mass is gone, and all I want are liters, which is a unit of volume. That's how I know I'm going to use the density. The density will get me from one to the other. So scrolling back up from the problem, it did give me a density. So that's hanging out right here. It technically also gave me a temperature. That's lovely. I basically am going to ignore that because there's no capital T in any of this mess. All I need to worry about is the fact that that's my density. So that's in grams per milliliter. So I have 100 grams. So I'm going to start with that of my solution. Then again, we want those grams to cancel. So since I have grams here on the top, I need grams here down in the bottom. So that's how I know that this is 0.079 grams per my 1 milliliter. So I know the grams go in the bottom because the grams have to cancel. So in order to get rid of my unit, I need my grams to go away. To make the grams go away, I need to have this in the top and this in the bottom. Now, before you hit the button, if you realize that you're like, oh, wait a minute, this is milliliters, and really what I want are liters, we could go ahead and add a third panel to this to remind ourselves that in 1 milliliter, there's actually 1 times 10 to the -3 liters. If you do that in 2 steps, that's completely fine. Either one will work. But again, then we can get rid of our milliliters too, because we don't want those either. We would like liters. 2.6582 liters. Shoot. Just going to zoom out a little bit because I write kind of big. Okay, so the goal was molarity. I need moles per liter. There's my liters. So I can now go ahead and solve this problem after, yes, what does seem to be a lot of work, because essentially for pretty much any of these concentration problems, you are actually solving 2 different things. So every once in a while you get away with not, but oftentimes you are in fact solving for 2 completely separate things, and then you get to divide one by the other. So these do not tend to be the shortest problems. 0 molar. So oftentimes people try to look for shortcuts. Honestly, these don't have shortcuts because you have to convert both parts, and that just takes time. So I'm still going to do the molality one. Were there questions about the molarity half? So I will still do the molality, don't worry. But were there questions about the molarity one I just finished?
There was no question about the molarity, but there is this other question that talks about what are the IMFs involved in the solvation process, and When given solution with different concentrations, how can we know which has a low freezing point, boiling point, or vapor pressure?
I have that one. So I'll go ahead and put a little asterisk by it because something like that was already submitted. So I will definitely get to that question as well. So I made some notes about some of the other questions that y'all have, and we will hit up those after I do the molality version. But it's part of the problem. So we're going to finish this real quick. The nice thing with molality is it's related to molarity in the fact that it is at least moles on the top. So nice thing, we already have half of what we need. So we're looking now for molality, same exact stuff, moles solute. We already solved for moles of solute earlier, and that didn't change. So we already have part of what we need. Then the only trick is this is now in kilograms of solvent. And remember that we're starting from 100 grams of solution with 70 grams of solute. That's what we started from. So in molality now, the thing is that we are having to deal with this idea of solution and solvent, but we're in mass. And y'all at some point learned about conservation of mass. So all we're going to do is say that my 100 grams of solution is equal to 70 grams of solute plus some grams of solvent. And I can just do the subtraction. And so I wind up with 30 grams of solvent. So I have the solvent part now. That's great. I need kilograms. So this is that part where I do need to be able to take my 30 grams and say that there are 1,000 grams in 1 kilogram. So I get 0.03 kilograms. So then that's what goes over here. So a lot of dealing with concentration units is looking at what you're starting with, in which case you just pick things that are convenient. I started with that 100 grams because we were doing percentages. If we started with molarity, I would have assumed that the bottom half of my fraction was 1 liter, because molarity is easy to assume that that bottom part is 1 liter. If I started with molality and I got to assume stuff, I would assume that I had a kilogram because it makes my life easier. But essentially you have to work with whatever you're given. So I usually just start with assuming that my given is the amount that I have. This usually makes my life a little bit easier. I have scribbled over everything, unsurprisingly. But we technically get 38.8 molal. So yeah, so there is not necessarily a magic in these. Folks are usually like, but how did you know it was 100 grams? I don't actually know that it's 100 grams. If you wanted to do 70% of 5 grams, if you want to do 70% of 20 million grams, you can, because the amount doesn't matter. 70% of 100 makes my life easier. So I just use 100. And that's just because of what we started with. That's all. So unless there are other questions, we'll scroll back up. And we're back to talking about polarity.
So we use the given density to convert to the milliliter from your given solution?
Yes. So when we were working with molarity, molarity from percent by mass wound up with us needing to go from a gram amount, which is mass, to a liter, which is volume. So since we were dealing with mass and volume, we use density. So yes, because we were trying to convert between mass and volume, that's why we use density. Yes.
And there is another doubt about the question that you recently solved. When you found the molarity of this problem, where will the grams go? Will you not add it to the 0.126850 liters?
So this is the thing, because the way that the definitions of our concentration units work. So the definition of percent by mass is grams of solute divided by grams of solution, technically then times 100%. That's how that is defined. So way back in the very beginning of chapter 13, we had formal definitions of all these concentration units. Similarly, when we did molarity, molarity is defined as being moles of solute divided by liters of solution. So that solute and solution in both cases, one, they match. So because I have solute to solute and I have solution to solution, I don't have to worry about when I'm doing percent by mass to molarity, I don't have to worry about any addition or subtraction, because that assumption of is this the solute or the solvent or the solution is the same. So the top part of the fraction is all about the solute. The bottom part of the fraction in this case was all about the solution. So when I did molarity, I didn't have to worry about any sort of addition or subtraction because everything was already taken care of for me. The other thing you need to watch is the fact we talked about that mass has a conservation of mass. You cannot add volumes together like that. You're not allowed to. Why can't I spell the word subtract? Oh no. For those of y'all that have been with me before, this happens with me in my OneNote. I did actually close all my extra programs so that this would not happen. So that's okay. Sorry, the thing on the other page. Try to get rid of my extra windows. But for those of you like, what was that? That was my budget. Because it's the beginning of the month, so I was doing budgeting earlier today. So we can atom subtract masses. So there is no such thing as conservation of mass, but you cannot, put that down again, you cannot add, I'll just use sub or subtract volumes. It's not a thing you're allowed to do. They don't work like this, mostly because molecules have this interesting tendency to interweave, and you don't necessarily get the same volumes if you just pour things together. I realize that this may be new information to you because if you worked in a kitchen, usually everything in your kitchen is water. And so if all you have is water, well, of course, 1 cup of water plus another cup of water is 2 cups of water. Of course it is, because it's all the same stuff. But when you're talking about solutes and solution, this does not work. 1 cup of sugar plus 1 cup of water does not actually get you 2 cups of sugar water once it dissolves. That is not actually how that works. You should try it out, by the way. If you don't believe me, try it. See what you get. There's also actually a really relatively famous one where you take 50, mostly because it blows people's minds when you do it. It's supposed to be a graduate cylinder. Roll with me. If you take 50 milliliters of water and 50 milliliters of isopropyl alcohol, you actually get something really strange. Still milliliters. You get something strange like 96 milliliters total. They don't add, and that's because of density. That is 100% because of density. The way that those molecules pack together is not necessarily the same in your isopropyl alcohol and in your water. And so when you bring them together, you don't necessarily get the same densities you had before. They don't just average. So volumes are weird, by the way. Part of the reason why whenever you spent time on density back in middle school, you can ask people about density again as adults, and adults get it wrong all the time because density is weird. Volumes don't add together like masses do. They just don't.
Somebody has also asked why you did not use density for kg of solvent.
So I didn't use density here because everything was already in mass. So the purpose of density, so when you look at the units of density, density is equal usually to grams per milliliter. So if I want to go in between mass and volume, density is fantastic. But look at what I was trying to do. I had originally, from the problem, I had 70% isopropyl alcohol by mass. So I started with this stuff. I started with 70 grams of isopropyl alcohol and 100 grams of solution. That's what I started with. So when I did molality, I started with 70 grams of solute and 100 grams of solution, and then I just needed kilograms of solvent. So this was already in mass, and I was headed to mass. So because I was still in mass the entire time, I left it with mass. Some of y'all might also be stressed out because you've seen other things that go from molarity to molality. That's not what this question asked me for, so that's not what I did. So this question gave me percent by mass, and so I went from percent by mass to molarity, and then I took a breath and I went from percent by mass to molality. So that's actually what I did in this problem. Some of y'all may have been expecting me to go from molarity to molality. I didn't. That's not what I did. So for those of you waiting for that to happen, that would be a separate question. I was given percent by mass, so that's what I used.
There is this one more question that when we have a given amount and we assume 1 kg or 1 liter, and we solve for the denominator using something like density or conservation of mass formula, what does the value represent? For example, if the molarity is 5 molar and we solve and find that there are 3.0 liters, how would that be possible if there is 5 mole per 1 liter?
So I'm going to go back to what I started with when I said that it's a concentration unit. So essentially the goal is to just give me a ratio. The goal is to tell me how much purple stuff do I need in an amount of liquid. So what we're doing in all of that is the goal is the ratio. So whenever we're reporting these numbers, we are reporting things in, here is my report in molal, which is reporting things in a kilogram of solvent. Here is my value in molarity, where I'm reporting it in a liter of solution. I was originally given it in percent by mass, where I was given it per 100 grams of solution. Those are, you're right, those are all different amounts, but they are all different concentration units. They are all different ratios, and they are the same as far as how much stuff per other thing do I have. I have to say other thing because 2 of these are in per solution and 1 of these is in per solvent. So yeah, we got different amounts because of the way we solved them. We solved them by separating out the top part and the bottom part. Because we separated out the top part and the bottom part, we had to make assumptions about how much physical stuff we had. So we made assumptions about how much physical stuff we had. And then at the end, we put it back together as a ratio. So that at the end, it does not matter that 9.2 molar is the same as 70% by mass. And since this is isopropyl alcohol, if you want me to, I can go run to my bathroom and get you a bottle of 70% isopropyl alcohol. It's what CVS sells. It's what Walmart sells. So that 70% by mass is the same. If I grab you my bottle from under my bathroom sink, it's the same percent by mass if we're talking about when the chemical company made it and they made it in a giant vat. And it's the same as to if you were a high school teacher and you actually got it by like the gallon jug. The ratio is the same. These are all concentration units. These are all ratios. So yeah, we made assumptions about the amount so we could do the math. But At the end, we're reporting ratios where the amount does not matter anymore. Other questions? This is the one time where I miss things being in person because I could see all's faces and be like, either you're bored or you're still confused, and now I'm just staring at a little green dot. Ha! Little green dot.
I think that were all the questions we had so far.
Okay. Because yeah, concentration units are weird because you just get to assume however much you want, and that is weird. I don't blame you. That is a weird thing. Okay, so back to intermolecular forces that was asked about. Also, I got a question about which will dissolve best in KBr. I didn't get the options for it, but I have KBr. So we're talking about intermolecular forces, including KBr. So one of the questions that tends to come up is something that involves, so first of all, IMFs, that was brought up in the chat, stands for intermolecular forces. So there was a list of these. These are also back in chapter 7. So the list in general for these is hydrogen bonding, dipole-dipole interactions. Come on, dipole-dipole interactions. Dipole-dipole interactions, by the way, was the one that I was demonstrating when I mentioned that whole like partial negative, partial positive, and the attractions in between. Technically, since I was using water, that was also a hydrogen bond because a hydrogen bond is just a really strong, and I'm going to say specific dipole-dipole interaction. Mostly because it's going to have a hydrogen connected to either, what do I want to go in order of? I'm going to say fun again. Hydrogen connected to a fluorine, a hydrogen connected to a nitrogen, I can't spell the word fun, or a hydrogen connected to an oxygen. There we go. The reason why I was contemplating that is they're also on your periodic table altogether. So whenever we're talking about hydrogen bonding, we are talking about a hydrogen atom that is connected to one of these elements. And essentially what's happening is these three are both so small and are so electronegative that what winds up happening is that your hydrogen that is connected to, say, my fluorine, that fluorine basically pulls so much of the electron density towards it. Yep, that's supposed to be an electron cloud. That this hydrogen is a little like extra positive. And this fluorine usually is a little extra negative, but the hydrogen is the one that we care about. This hydrogen then is a little extra positive. It also usually is physically smaller because of all the electron density the fluorine has pulled away from the nucleus of that hydrogen. So that hydrogen usually can also get a little bit physically closer to other interactions, which makes the interaction stronger. So hydrogen bonding, dipole-dipole, London dispersion or just dispersion forces, which this is the thing that everything has. If it has an electron cloud, it has this. So everything has these. And then the other one, and we could have a philosophical debate about whether they count or not. I'm gonna put them over here, but I'm just gonna put that's stronger than all of these, because I'm basically gonna call this not an intermolecular force, because that's my personal opinion, would be ion-ion interactions. But like I said, yeah, you can get people with PhDs to sit around and argue about if an ion-ion interaction counts as an intermolecular force or not. Because essentially all we right now really care about is attractions. And an ion-ion interaction is definitely an attraction. So whether it's an intermolecular force or not does not matter, because ions are definitely attracted to other ions. But you may have noticed when I was drawing these little squiggly lines, I kept saying the word partial, because in a molecule where, let's draw a different one. So here's my carbon with 2 chlorines and 2 hydrogens, and we've got more negative stuff down here and less negative stuff up here. It's not a whole charge. There's more negative stuff on one side than the other, but there's no like missing electrons. There's no extra electrons. It's just an uneven distribution. Ions are where you actually have a positive thing and a negative thing, and that interaction is going to be stronger than any of your other things, your hydrogen bonding, your dipole-dipole, or your London dispersion, because they're whole charges. We could get fancy, by the way, and talk about this as lattice energy. So for those of you that are like, when did we ever talk about ion-ion interactions in Gen Chem 1? This was actually a chapter 5 topic, and it was lattice energy. So yes, we did. It was back in chapter 5. So it is in a different chapter than these other ones, but all that we're trying to actually ask now is, so when you put stuff in solution, what happens? So oftentimes what we ask is, if we wanted to say something like, here's KBr, and we're asking what KBr will dissolve best in, we are actually looking for something that has the same intermolecular forces or has the same attractions. So this is the part where when you're looking at KBr or potassium bromide, what you should notice is here's my K and here's my Br. I have a metal and a non-metal. The left side of the periodic table, the right side of the periodic table. Something in green, something in blue. Something shaded as a metal, something shaded as a non-metal. Your periodic table that we give you is color-coded. So because of all of that, this is an ionic formula. This is an ionic compound. So therefore, if we're asking what it dissolves best in and I want the same attractions, I'm looking for something that also has ionic interactions. So even though it seems weird, if I'm asking what does KBr dissolve best in, and I have stuff like water, because everyone loves water, and I have carbon dioxide, and I have, say, sodium chloride, I want the other thing that's ionic. Yeah, I know water's called the universal solvent. I kind of wish it wasn't, because it's not. We don't dissolve in water. You ever thought about that? Like, your clothes don't dissolve in water. We do not dissolve in water. Hopefully when you put your cups and plates in the dishwasher, those don't dissolve in water. Water does not dissolve everything. Just FYI. So I want the same attractions. So if I've got KBr, which is an ionic compound, I want the other ionic compound. So I would actually want something that's also ionic, if that's what I'm looking for. Water, we already mentioned, both has that dipole-dipole interaction. It also does have hydrogen bonding. So if I'm trying to talk about something that dissolves best in water, I want something that has hydrogen bonding. That's going to be what dissolves best in water. Yes, lots of things dissolve in water, lots and lots and lots of things. If it has hydrogen bonding, it's going to dissolve best. And that word best is typically what we're looking for. Carbon dioxide, we drew earlier. This is the one that is only going to have London dispersion forces because it just has, because it's a nonpolar. So that idea of polarity and intermolecular forces do also go together. Now, one thing I'd like to point out is on the exam, what we usually do is we often ask what dissolves best in this. So this question I started with of what does KBr dissolve best in, this is often the question we ask. Not always, because we write new questions all the time, but often we use something like this. It doesn't actually ask you what the intermolecular forces are. You have to identify them. But if you learned different terminology for those intermolecular forces, as long as you can still identify, I have a polar thing with special stuff, and I have a non-polar thing, and I have an ionic compound, that identification is what you need. It's a matching game. So yes, identifying all the intermolecular forces is useful because it's important to figure out that water and carbon dioxide do not have the same intermolecular forces. So you do need that information. And yes, I went ahead and used all of that language. But technically, if the only question I'm trying to answer is what does KBr dissolve best in, all I need to be able to recognize that potassium bromide is an ionic compound. That's whole charges. So therefore, when I'm looking at my list, I'm also looking for whole charges. That's what I'm looking for, and that's what I want. Questions on that? Not hearing any. So if we change our minds, that's okay. I know it takes time to type things in. And as you might have imagined, there are lots of different examples of this. So we could again spend 20 minutes just on this kind of style of a thing because we could talk about all the different things that could dissolve in other things and lots of different examples. That idea of examples is often why we recommend things like the end of chapter questions at the end of the textbook, the end of the chapters of the textbook, and Alex, because it usually helps with practice of different ideas. Not hearing anything, so I'm going to scroll back to my big list. Yes.
For ion formation, I was wondering why the bigger compound is more likely to form ion pairs than another compound with the same charge that is smaller. This sort of goes against lattice energy.
Okay, so the bigger compound. So I'm going to assume that y'all are talking about this question, where we're talking about ion pairs. Where is my home button? Where's my home button? So I assume we're talking about this one, where we're talking about which ones are more likely to form ion pairs in water. So first of all, whenever we talk about ion pairs, that general idea is the fact that usually when you are starting off with an ionic compound, you've got a positive and a negative and a positive and a negative and a positive and a negative. And this is a solid, by the way, that I'm trying to draw. A negative and a positive and a negative and a positive and a negative and a positive. And this actually extends in a cube. So there's even more of them. That what happens is we typically assume that then when you throw this into water, that we get all the individual ions and that this will then be surrounded by water. I'm just going to draw not all the water molecules. I'm just going to draw some oxygens with some dashed lines to make my life a little bit easier, because otherwise I'll be drawing forever. So essentially, this is what we usually assume, that things get completely separated. But when we are talking about ion pairs, that is then what hopefully it sounds like, which is when we throw things into water, that we will have some things that actually do stay together. Not enough that they don't dissolve, but so you still have some positives and negatives that are hanging out by themselves, but some of them are actually together. I should not have drawn those overlapping. I don't like that. They should be next to each other because they're still attracted to each other. So there's a couple of things that will usually make things more likely to form ion pairs. One of those is just the fact that the more pieces you have, oftentimes the more likely you are to get ion pairs. That has a lot more to do with the idea that there's just more pieces, and so the probability that some of those pieces came back together and found each other again is higher. There's more pieces to deal with. Then I'm actually not certain what you're talking about with size, because the next thing I was going to go to was looking at this notion of dealing with a little bit of Coulombic forces. Sorry, these are my notes from class. And so a lot of times what you see when you see things like Van Hoff factors, which is one of the other ways that you can investigate things like ion pairs, you're usually then talking about what the charges are of those and how readily they are to actually go ahead and separate. So you usually see things where things like so your sodium and your chloride, where you have a sodium with a +1 and a chlorine with a -1, usually has fewer ion pairs than something like this is a magnesium sulfate, where your magnesium has a big +2 charge and your sulfate has a big -2 charge. Those giant charges are more likely to find each other, and they're more likely, therefore, to still be paired together. So I was actually going to head back to lattice energy. So the part where you're saying lattice energy doesn't work confuses me. So I don't know if that's something that we need to talk about more in office hours to go with this. As far as size, back from chapter 5, there were two things that we dealt with lattice energy. One of them was size, the other one was charge, and charge always mattered more. Charge always mattered more than size. Size affects things, don't get me wrong, but charge was more important than size. Back with lattice energy. So essentially, things that have higher charge more likely to form ion pairs. So a higher charge is, again, something I should be able to remember. It's back from chapter 5, how you would know, but remember that there are things on the periodic table that can help you out. So a reminder that everything in group 1A has a +1 charge, group 2A has a +2 charge. The stuff in the middle is variable, and there was a whole list of things like polyatomic ions. So for those of you that were like, wait a minute, how on earth did I know that sulfate was a -2 charge? That's a polyatomic ion, also hanging out in chapter 5. In general, whenever we say things are cumulative, one of the things that y'all will be working with is the fact that your instructors have a certain amount of chemical literacy, that we just consider certain things to be everyday language. So polyatomic ions are kind of on that list of everyday language. Sulfate, phosphate especially, those get used a lot of times in various buffers, or we talk about like sulfate compounds out in the environment. So there's especially polyatomics that are frequently utilized either in buffers in the lab or that we see around us.
We do have a couple of questions.
Okay.
I was wondering why something that is more soluble would have a lower freezing point rather than glucose that is less soluble. Does it have to do with IMFs or something else?
So solubility and just different things in water? So solubility and why things are more soluble than others?
I guess that's the question. And we have another question asking, how do we tell the charge again?
Okay. So as far as telling charge, there are things on the periodic table that will help you out with charge. So group 1A being +1, group 2A being +2. There are also ways then with your polyatomics then to basically kind of unravel what the charge is. So for example, if I had iron, I'll go back and still use my sulfate. Iron is hanging out here in that block with where there's a whole bunch of different potential charges. So this is the one where I need to be able to recognize the fact that sulfate, this SO4, is a polyatomic ion that has a -2 charge. Because this is an ionic compound, unless I'm told otherwise, which if being told otherwise would mean that there would be some sort of like -3 charge for like the whole thing, which that doesn't exist. So unless you see a charge, you assume that this is neutral. So the assumption is that this compound is neutral, which means that if I have a sulfate with a -2 charge, that means my iron, I basically have -2 from my sulfate. The whole thing has to be 0, and my iron has to be something that will cancel out a -2 charge. So I essentially wind up with x minus 2 is equal to 0. My x winds up being +2. My iron, therefore, is a +2 charge. So being able to unravel those and think about what the charges might be, where those might come from, again, periodic table will help you out. If it is in that big block, then oftentimes you're going to be dealing with either non-metals, where similarly there were non-metal charges. 7A is -1, 6A is usually -2, 5A -3. 4A starts to get really wonky. So carbon usually is -4, but carbon usually is in covalent compounds and is not in ionic compounds. So those are some of the ways that you can know what the charge is. So polyatomics have set charges. Then my non-metals here have usually set charges. Metals also have their set charges. If you're wondering what that's from, that is all from chapter 5. Yes.
Somebody has also asked if ion-ion interaction is different from ion dipole. How would they stand on IMF's strength scale?
So we'll come back to this. So as far as ion dipole, so first of all, you noticed that I didn't put it on here because the only reason we care about ion dipole is it's the reason why salts dissolve in water. It's the reason why salts dissolve in anything, because essentially those times where I had a positive charge and I said, and now my water would have that partial negative charge aiming at the ion. That's how this works. This is an ion dipole interaction. So as far as how it ranks, it essentially ranks usually higher than most everything except for the ion-ion interaction. So this usually is still better than hydrogen bonding, but we kind of start to cross the line into which one's going to win. So that's usually why we cover it separately, and we don't usually throw it in here because it really starts to matter exactly what's going on and exactly what everything is. So at the beginning of this chapter, there was information on both enthalpy and entropy and how that played a role in how things dissolve. And so the tricky thing when you start to get in with ion dipole interactions is you often are actually trying to think also about things like the enthalpy of solution and what all the competing factors are. We covered ion dipole last semester just so that then when we started to dissolve things, you weren't like, whoa, stuff interacts with other stuff? Yes, stuff interacts with other stuff. So yes, ions do interact with things that are partially charged. We could actually do some interesting mathematics with this if you wanted. That's usually stuff that we save for physical chemistry. because a lot of times exactly what the charge is and how well it interacts with exactly what the dipole moment is, you start to need to get into higher level mathematics in order to talk about this in a way that's more meaningful than, hey, it happens. So all we really need out of ion dipole is just kind of the, hey, it happens. Ranking it gets tricky very quickly.
There is also one question which asks about the ion pairs forming. Which one would have a higher chance of forming ion pairs? Potassium bromide or lithium bromide, KBr or LIBr?
So the question is, which one of those two does a better job? So I was going to go back to the reason why I'm hesitating like this is that's really granular. And I mean, we can do it, but honestly, we're much more likely to ask y'all to solve for their Van Hoff factors than we are to ask you to throw back to lattice energy, because lattice energy is how you would solve for that. And we are way more likely to give you data and ask you to use the Van Hoff factor. So this question, while it's interesting and it's conceptually valuable, the difference in between those two really is mired in lattice energy. So I will make myself a note, and I'm happy to make a separate video that goes all the way back into lattice energy. But honestly, I have 45 minutes left, and they're different. You talking about the Van Hoff factor is more valuable to you than talking about the differences in between those. So I will make you guys a separate video, but that's really not worth my time right now. We need to move on from ion pairs. Because ion pairs are valuable as a concept, but how to rank them is really a chapter 5 question, and we aren't in chapter 5, we're in chapter 13. Okay, so one of the questions that came out of the chat that's been a while now that I didn't get to answer was about solubility in general. So solubility in general, when something dissolves in water, there are a couple of components. There is both an enthalpy component and there is an entropy component. So there are two different reasons that something will dissolve in water. Enthalpy has multiple components itself. So enthalpy is the one where we looked at the delta H of a solution and we said, all right, in order to make enthalpy happen, there is going to be an enthalpy of where you are breaking solute interactions. And since we are breaking solute interactions and we are tearing the solute into little tiny pieces, into its individual molecules or into its individual ions, that's going to require energy, which will make it positive. We're also going to have breaking apart my solvent-solvent interactions. So that would be a positive value. This is a positive value. We technically add them together. And we technically are also adding, even though it would be a negative value, because we are forming. Forming is negative. The solvent-solute interactions. So just trying to talk about why does something dissolve in something else, we usually have to talk through the fact that you have to have the formation of interactions between the solute and the solvent, which then could be that ion dipole interaction, but the formation of the interaction between the solvent and the solute we would like it if it was better than the energy required to break apart all the solvent-solvent interactions or to break apart all the solute-solute interactions. So that delta H of solution is part of what matters. I think the person, when they were talking about this, mentioned something like sucrose and water, and table sugar does have a lot of hydrogen bonding. And because of all that hydrogen bonding, the nice thing is that a lot of times, the more similar the IMFs, the more similar those intermolecular forces are, usually in general, the lower your delta H of solution is. And when I say lower, I really mean closer to 0. Let me get specific, not more negative. I mean closer to 0. So whether it's a little bit positive or a little bit negative, the general notion is that the more similar the intermolecular forces, the closer that value is to 0, which means that things then are probably going to rely more on entropy. Now, we're going to spend a lot of time on entropy later on in the semester. For now, really the only thing y'all need to know about entropy is this is where essentially, this always sounds silly when I say it, more options, more better. So you may have learned about this as chaos. This is not my favorite version of this, but I usually say it because for folks that are like, oh, you said chaos, that's what entropy is. Really, entropy is the idea that nature prefers things to be as spread out as possible. Nature prefers things to have as many options as possible. Entropy is the main reason why you never worry about all of the oxygen in the room suddenly being at the top of the room, because you expect the oxygen in the room to be evenly spread out. You expect the oxygen to be in as many places as possible. You do not expect the oxygen to have suddenly coalesced into one big dense block all in the top corner and suffocate. It doesn't do that. Nature doesn't do that. So a lot of times, entropy is the real reason that things dissolve, because oftentimes our enthalpy value is so incredibly close to 0 that, I mean, it matters. It influences it, but not a lot. Oftentimes, entropy is the main reason why things dissolve. So as far as why do things have different solubility than others, one, you're still balancing both of these factors. So you are balancing both the enthalpy and the entropy. They both matter as to why something dissolves at all. And then enthalpy then is still broken down into a whole bunch of other factors. So asking why something dissolves better than others is a great question. And some of that you can talk about really well with the different pieces of your delta H of solution. But a lot of times you can still have a solution that's overall endothermic, requires energy to dissolve, but definitely dissolves. And that's where that entropy is actually your guiding principle, because essentially more options, more better. So the more options you have, the more entropy you have. How are we doing on questions now? I got cut up from the chat.
There is this one question. If you can clarify the interaction between solubility and freezing point. And somebody also asked you if you could walk through the justification for the answering the ion pairs practice problem.
So yes, I will go. Can somebody put in the chat which number that is? So I will go through the practice problem and I will make you guys a separate video. So yes, I will apparently go through that with a fine-tooth comb in a separate video.
And the early question was about the freezing point and the solubility. The interaction between somebody wants to know that ask you to clarify between the interaction of solubility and freezing point.
I'm thinking. I'm thinking.
Yes.
Okay. So we have already spent time discussing solubility and why some things are more soluble than others. And the fact that in order to talk about why something is soluble and how soluble something is, these things will matter. There are more things that go into how soluble something is. This stuff matters. There is also stuff that we did not talk about that would go into things, especially like ionic compounds, because some ionic compounds are very easily soluble. Some of them are not easily soluble. So so there is more stuff into why something is soluble. So even the amount that I ranted about this, I still left off how you can have some compounds that are ionic and have things that have the exact same charges but have a completely different solubility. So I am ignoring that for right now. That's a fabulous office hour question because I need to dig out my Chem book and then show y'all some like interesting partial derivatives or partial integrals. I forget which one right now because some things will have the exact same charges but have different solubilities. You've probably already seen that. So as far as how solubility and freezing point interact, the bottom line is they don't. So solubility is controlled by stuff we just talked about. Solubility is controlled by enthalpy. Solubility is controlled by enthalpy, entropy. It's also, we could also spend time talking about charge density, which we will not test you on. We could also talk about, oh gosh, there's another Greek letter. I'm so sorry, I forgot. I'm just going to say the junior level Chem class, junior level physical chemistry. So there is more stuff that goes into why things dissolve. Freezing point. Freezing point is just cares about how many particles are in solution. It doesn't care how they got there. Doesn't care. Freezing point doesn't care if the particles are in there because it was more favorable because of enthalpy, or if the particles are there because it's more favorable because of entropy. Freezing point doesn't care. Freezing point just knows how to deal with it once they're in solution. So freezing point doesn't care if those particles are sugar, or if those particles are salt, or if those particles are a gas. Doesn't matter. Freezing point only cares how many particles are there. So solubility is complicated. Why something is as soluble as it is complicated. Freezing point is not. Freezing point is just how many particles are in solution, and then essentially what happens is those particles just get in the way of freezing. So as far as your freezing point goes, realize that whatever you are going to have freeze, and yes, I'm going to draw water again because it's relatively small molecule and it's therefore pretty easy to draw. So typically those water molecules will align based on their dipole moments. If they also have to mess with a charge, then those hydrogen bonding interactions have to also mess with a charge at the same time. So the nice, pretty crystal structure that you would expect in an ice cube gets disrupted by whatever other particle is there. This could have some interactions with intermolecular forces, but overall, a lot of times what's going to happen is you're just going to have the physical issue of messing with Legos, where everything should be all nice and pretty, and then there's this marble that's stuck in there, and you have to realize that it's then not going to be as pretty because you have to make an accommodation for whatever this other thing is. And this is essentially going to then change your freezing point because your water can't just be in the nice, pretty crystal structure that water does when it's by itself. It has to accommodate whatever other particle you have. So hopefully that clears up that connection, because honestly, you're trying too hard. So this is one of the fascinating things in chemistry is that, yes, there's some pieces that go together, but this is one where the deeper you go, the solubility well is very deep. Why something is soluble is a really deep well. There's a lot of stuff there. Freezing point, you actually just run into a really physical issue where stuff would like to interlock with its interactions and go together in nice, neat, orderly ways, and it can't always because it's got something stuck that it has to work with. So freezing point is a much more physical issue than solubility. Solubility has a lot of components and a lot of pieces. Other things right now.
Somebody has asked, what if you're given different concentrations with different compounds and asked to compare? Do the concentrations matter before anything else?
I need more information. Asked to compare what? Oh, so I'm so curious. Here's my assumption. Unless they've got, I have an assumption unless they have a clarification. Because I assume we're talking about something where we have, let's say, we'll do molality, where we have a 2 molal solution of sodium chloride, and I have a 2 molal solution of, we'll just go with glucose, it's a sugar, and I have a 2 molal solution of iron 3 chloride. And then the question is, which has the lowest freezing point? So I assume that this is where we were going. So in this case, all of my concentrations look like they're the same, but they're not. My sodium chloride, I think we've already mentioned, when I throw this into water, I'm actually going to expect this to break into 2 pieces. I have a sodium ion and I have a chloride ion. That's 2 pieces. So really, there's this Van Hoff factor I, and I would expect this to have a Van Hoff factor of 2, which means when I'm really thinking about this salt solution, this is really a 4 molal solution of particles. I got 4 because I already had a 2 molal solution of sodium chloride, but when that sodium chloride breaks in 2, I basically took my 2 molal, multiplied it times 2, which is my Van Hoff factor, and I got 4. Same thing with my glucose, that's all carbons and hydrogens, that's all going to stay together. That Van Hoff factor is just 1. So my glucose then is a 2 molal solution, and it just stays all together. There's no ions to separate, nothing interesting happens, you just get a 2 molal solution of particles. I have my iron 3 chloride. I would expect there to be an iron, and I would expect there to be 1, 2, 3 chlorides. I know that because of this 3 right here. That's 4 particles in total. So when I'm looking at my 2 molal solution, I would be taking my 2 molal solution of my iron 3 chloride. It's going to break into 4 particles, so that's 2 times 4, or an 8 molal solution of particles. So now, if I care about freezing point, what did it ask me for? Lowest or highest? So whenever we talk about freezing point, this is supposed to be freezing, the colligative property is called freezing point depression. And freezing point depression means that basically the more you add, the more particles, the lower the freezing point. So essentially, for my concentrations, we took each one of them, we considered how many particles they all break into, and essentially what our new concentration would be, the one, because it's freezing point depression, the more particles, the lower the freezing point. If my goal is to find the lowest freezing point, that's the one with the highest concentration of particles. Hopefully that's what that person was after. If not, then I need more words. And I arbitrarily picked the lowest freezing point. So for those of you that are then thinking, well, what about the highest freezing point? We basically do the general same idea, in that we are still caring about the actual concentration in terms of how many particles are there. But if I wanted the highest freezing point, then I want the one with the lowest concentration, which then would actually be my glucose. So glucose, my 2 mol solution of glucose would actually be the highest freezing point, which sounds kind of strange because it's freezing point. But the warmest freezing point would be the one with the lowest concentration. How are we doing?
How do we know glucose only breaks into one molecule?
So a lot of times the way that you'll know, there's a couple different ways. So one way is we could tell you, hey, this is C6H12O6. We could give you the formula. This has no metals in it. This is not ionic. And it starts with a carbon. So this is just all molecule. So one way that you could know is we could give you the formula and you would know from there. The other way you might know is we could describe this to you as a non-dissociating solute. So we often describe things that don't break into multiple pieces as a non-dissociating solute. Fancy way to say you only get one piece. It has a Van Hoff factor of 1. That's just what that means. So dissociation means that it would fall apart into multiple pieces. Therefore, non-dissociating means it doesn't fall apart. So those are the 2 main ways I can think of. Oh, we could also, doesn't happen often, but it does happen. We could also just tell you that glucose has an I equal to 1. So I realize that last one may seem ridiculous, but it is entirely possible that we'll just be like, oh, by the way, this has an I of 1, or assume it has an I of 1. Again, usually we do other things like give you the formula or use the phrase non-dissociating solute, but you never know. We might just say, by the way, this has a Van Hoff factor of 1. So that's also an option.
Somebody also wanted to see if you could go over the starred question.
Sure. I would love to get back to the outline I made at 2:30 this afternoon. How to tell which aqueous solution will have the lowest or highest boiling point. So this one is asking about boiling point instead of freezing point. So what I'm going to do is use the same general information that we were working with, because we've already done a lot of work for this. So if we in fact had the same general set of solutions, but now I wanted to ask instead, and I wanted to say, what about the highest boiling point or the lowest freezing point? So the phrase is boiling point elevation. That's the name of the colligative property. That means that the more particles you have, the higher the boiling point. So because the more particles you have, the higher the boiling point, what we're going to do is go ahead and again find my concentrations for those same solutions. So the one where I had an 8 mol solution of particles, this is the most concentrated. This has the most particles. Because it's the most concentrated, more particles, higher boiling point, most concentrated, this is the highest boiling point. So the highest boiling point and the lowest freezing point actually go together. So lowest freezing point is also your highest boiling point. Likewise, whatever we said was our highest freezing point, this is also going to be my lowest boiling point. So the thing that had the lowest concentration is also going to be my lowest boiling point. So boiling point elevation, the more particles you have, the higher the boiling point. Boiling point elevation, so the more you're basically influencing that colligative property, the more particles you have, the higher it goes. Freezing point is the opposite. It's freezing point depression. The more particles you have, the lower the freezing point goes. This is the nice thing with remembering the names of the colligative properties, because those colligative property names do actually tell you which way they go. The more stuff, the lower the freezing point. The more stuff, the higher the boiling point. There is a part of chapter 13 in the very beginning that talks about how that could be when you're first introduced to freezing point and boiling point. And what it does is it talks about the fact that if this is my phase diagram, both my freezing point and my boiling point change, because essentially my solution stabilizes the liquid. So we talked a little bit earlier about how when things are trying to freeze, the solute particles physically get in the way of freezing. So therefore, you have a liquid over a longer temperature range because things physically get in the way. That's actually the same general idea behind boiling point elevation, except now the thing that's physically getting in the way is still your solute, but it's physically getting in the way of your particles escaping into the gas phase. So essentially, all of that surface area on the top of your liquid is basically some of it's being blocked by solute particles, so it's not as easy for the liquid to escape into the gas phase.
Somebody has also asked, when trying to get the highest or lowest freezing point, we can just choose based on the molecule's solubility or electrolyte itself instead of doing calculations.
So I feel like I've already talked about why solubility and freezing point are separate ideas. So if you need more about why solubility and freezing point are not directly related, then we need to sit down and talk about where your confusion is. Because we've already discussed the fact that solubility is separate. The reason why I went ahead and did a calculation, so granted, I made up this example. That is true. So if I make up another example, we can have one where I have a, still use ones and twos, where I have a 1 mol solution of sodium chloride. I have a 2 mol solution of glucose, and I have a 1.5 mol solution of that iron 3 chloride. Now they're not all the same. So now we might actually need to worry about that calculation that I did. Now, you don't have to calculate the actual freezing point. So if the question is, do I need to go ahead all the way out and calculate freezing point? No. We answered this question earlier by just looking at what the I value was and what the new molality would be. And we never actually calculated the freezing point or the boiling point of anything. But we did consider a 1 molal solution of sodium chloride is really a 2 molal solution of particles. A 2 molal solution of glucose is really a 2 molal solution of glucose. So those two would actually be the same. A 1.5 molal solution of iron 3 chloride is going to be a, double check and make sure I get my math right, 1.5 times 4, a 6 molal solution of particles. So that's just taking the molality and multiplying it times my value of I. So that's all I was doing in that case to make a comparison. So that sort of calculation you might need to do in order to actually compare what's got your highest boiling point or your lowest freezing point. And yes, I understand that in this example, 2 of these are actually the same. So these 2 would be the same. One of these is different.
There is this also one question in the chat. Wouldn't you need the KB or KF to determine the new lowest or highest boiling point, given that they are different species?
So if you would like to, you can do it that way. So if this math makes you uncomfortable and you would much rather plug into the freezing point formula, you can do it that way. Here's my I, here's my KF, here's my molality. Essentially, because the goal was highest or lowest, and the goal was not what's the new number, what winds up happening is you just do a lot of math. And all you're really changing is you're changing your I value and you're changing your molality. If you are not convinced that if all you need to do is rank is that, and you feel like you need to solve for the new freezing point, solve for the new freezing point. Got a pencil, you got a calculator, you got paper, go for it. So if you feel the need to solve for the new freezing point, you can. But what I'm telling you is we would be assuming that these are all in the same solvent. So I apologize that I did not. So this is the only hard thing when we pull stuff out of the chat and I'm trying to guess exactly what the question is I didn't write the question. So we would be assuming that all of these are in the same solvent. So we would assume that these are all, let's say they're just all aqueous. So we would just assume that these are all aqueous, every single one of them. So that way we're in the same solvent. So I do apologize that I did not make that clear from the beginning, because I didn't write the question out. Because when I first started this problem and this rabbit hole, I was guessing what the person was asking out of the chat. So my apologies. This does assume that the KF value is identical for all of your solutions. This does assume that these would be all the same solvent. I'll go back and write that over here, assuming same solvent. So yes, you're absolutely right. This does assume that you have the same solvent, so that your KF value would be identical for all of these. And that's the reason why this was working, is because we were assuming that everything was the same solvent. So yeah, my apologies, I did not make that clear in the beginning. I have to X out of this again because this is not. There we go. Okay. So assuming they're all the same solvent, That's what all this was doing. Otherwise, yes, then you have to do much more math. One of the things we often try to do on exams is we often try to test one concept at a time. Not necessarily say we'll always do that, but essentially, if we're looking for the final freezing point, we're usually going to ask you for the final freezing point and test your ability to go ahead and plug things into the equation and go ahead and figure out, okay, it's freezing point, so my freezing point needs to get lower. Can you pull the right freezing point? Can you do the subtraction? Can you get to the new freezing point? If we're trying to do a comparison, then oftentimes what we're really looking for is that concept of the Van Hoff factor. So we typically just ask you about, to compare things that have the same solution and that have the same solvent, so that you're really actually trying to consider the Van Hoff factor and you're not trying to consider the Van Hoff factor and a variety of different solvents at the same time. So, my apologies, I did not do that from the start. Okay, what have we talked about from my original list? So we did talk about entropy and enthalpy. We did do that. We did talk about what will dissolve in KBr. We talked about heat of solution. I am going to make a video about this because I did not realize that that this was so confusing. So video on ion pairs coming soon, because apparently that requires more than I anticipated. We talked about figuring out how you assume 100 grams versus 100 versus 1 liter. We did the example problem with rubbing alcohol. I did most of what I anticipated doing with Van Hoff factors and examples, because we talked about different values of I. There is one version I was going to do that I have not done though. So speaking of Van Hoff factors, I'm going to go ahead and grab the one that I didn't do. So this says a mole of an unknown salt is added to 1 kilogram of water. The boiling point of the solution is 100 degrees Celsius, 100.7 degrees Celsius. It's kind of awkward wording. Sorry about that. What is I? So it's just flat out asks you, what is the Van Hoff factor? So your text, so I'm going to solve this 2 ways. I'm actually going to solve this the way your textbook solves this first. So your textbook goes ahead and says, all right, so the definition of I has to do with the actual molality divided by, I forgot what they call this. I'm going to call this the formula unit, the molality. I don't know, formula unit molality. But essentially what we're going to do is, they said in the problem that they went ahead and dissolved a mole of an unknown salt into 1 kilogram of water. So that's going to be my formula unit. So essentially they took 1 mole, they just divided that in, dissolved it in 1 kilogram of water. That is in fact just 1 molal. Wouldn't you know it, I made the math easy when I made the problem up for myself. So this bottom part is basically, you went to the shelf, you measured stuff out, this is what you got. You could also call this the undissociated, oh, this grammar is kind of painful, the undissociated molality. It's the molality where you assume the I is 1. We don't know what the I actually is, but this is where you just assume that whatever they gave you is not worrying about dissociation. And that's what goes on the bottom part of that formula that's out of your textbook. So the information they gave us is about the boiling point. And it said water. We know that the boiling point of water alone is 100 degrees Celsius. And we know that the boiling point of the solution is 107. So the boiling point of my solution is 107. And I know that that's the boiling point of my water plus change in temperature. So therefore, I can go ahead and subtract and find that my change in temperature is 0.7, and this is degrees Celsius, apologies. So 0.7 degrees Celsius is my change in temperature. Now what I can do is I can use this idea of boiling point and I can solve for the actual molality. I can solve for the molality that would happen once everything is dissociated, the molality that happens once everything comes apart. So I have my change in temperature. That's my 0.7 degrees Celsius. And I'm just going to use molality times my KB for boiling point. Now this is the part where KB would either be in the problem or it would be at the top of the page in potentially useful information. So those are the two places where you would find KB. Either it's in the problem, in this case it was not, or it would be on your potentially useful information page. In this case, I cheated and it is written in the notes by my side, 0.52. You do not have to memorize it. It would be in one of two locations. So now I can go ahead and solve for this. 0.7 equals my molality times my KB, 0.52. My actual molality is 1.34615. So then I can go ahead and take my actual molality, divide it by the undissociated molality, which yes, is just 1. But you at least get a better handle on how this particular equation works. So I should just do that in 3 sig figs, apologies. I equals 1.35. So hopefully that at least gives you a look at one of the other ways you can calculate I. Yes, there is another way. If you had the same general setup, the way I frankly usually do it is still using that change in temperature formula, but then I usually just go ahead and stick the I in there. Your textbook doesn't always do it that way, but essentially if you did it this way, it's still the 0.7, and there is the I, the K is still the same, the 0.52, then your molality, you're using the undissociated molality that I was trying to talk about, undissociated. That's not how we spell anything, but that's fine. Which was that 1 molal that we mentioned earlier, you get the same answer. So either way will work, but I know oftentimes when you guys are looking at end of chapter problems, the book does it with the formula they gave, and then there's oftentimes a little bit of confusion over this idea of actual molality versus the other one, and they're just trying to talk about undissociated versus a dissociated molality or molarity. Both of those work. Anything else?
Somebody has asked why is delta T is equal to 0.7 instead of 0.3?
That's because I made up this problem and I used 100.7 for my delta T. So if there's another version of this problem that uses 100.3, but basically the question that I made up has a boiling point of 100.7. And so therefore I subtract 100.7 minus 100 to get 0.7, but that all came from the problem that I made up. So if there's another version of this problem that's very similar, that's in either Alex or the end of chapter questions, great minds think alike, but I made this one up at 2:30 this afternoon. So that's where the 0.7 came from. It was given in the problem. Other questions?
Yeah. Since I thought, okay, there was a question. Never mind. Sorry about that.
No, it happens. Reading out of the chat can be tough. I don't know if you were in that fun year last year where I was the one doing the moderating chat for Dr. Diekman. And he would ask things like, are there any questions? And I would be like, or there would just be silence while he's waiting for me to like figure out what to say. So no, I get it. I've done your job before. It's not easy.
I think you have answered all the questions so far. We don't have any more questions.
Okay, cool. So here's the deal. There were still some questions from the things that were submitted earlier that I have not talked about. So a couple things. One, I will go ahead and do a video on whatever this problem is that is apparently out of the end of chapter questions that I did not realize when I pulled it because it was just plopped in. Then the other things that were asked for was a review of vapor pressure, a Raoult's law practice problem that I made up, and talking about the ideal solutions graphs. So I will go ahead and make a video that does those pieces as well. Here's the one thing though. Whenever people ask me to do a review of stuff and I'm the one who did the pre-recorded content for it, I am going to remind you that there are videos that are posted that are about the pre-recorded content. I prepared material for this, even though it's a repeat, so I'm happy to do that. But anytime I'm the one that made the pre-recorded lecture videos, I just want to give you guys that general warning that if it sounds really similar, it's the same person. I realized I had a haircut then that I don't have now, but it's the same person. So I did make stuff from scratch so that it will be different, but it might sound really similar because it's still me. And sometimes I can't hide the fact that I'm still me. I try to say things in different ways. I do. So I will make a video off of that stuff. And then the other thing I do want to mention in these last couple minutes is, one, we did not talk about everything in chapter 13. So one of the things that happens in these reviews all of the time is that there's no way for me to condense 3 weeks worth of material into 2 hours. It does not work. It does not happen. So as y'all noticed, I did my best to take questions out of the chat. I know sometimes I get a little bit frustrated, but that's part of that is because I'm trying to both think about the question, answer the question, and then I do things like forget to say all of the solvents are the same, and then I feel dumb because I forgot to give really useful clarifying information. So one, this is not everything, and two, we only talked about chapter 13. In these 2 hours. I only did things out of chapter 13. I did not do anything out of chapter 14 in the past 2 hours. So especially for those of you that are like, oh, I'm feeling pretty good. I'm glad you feel good if that's you. Do realize that we didn't mention kinetics. So we didn't mention anything about the speed of a reaction. We didn't mention anything about how long does a reaction take. We didn't mention anything about K or units of K, the rate constant, the rate law. We didn't do any of that. So there is still a lot of material that is still coming that will happen next week. And there's still a lot of stuff to guys to go over. So just keep those things in mind. That yes, we did cover a lot of things in 2 hours, but we did not cover everything in 2 hours. Anything else? Otherwise, we're 5:59. And I try to be respectful of everybody else's time who's doing the wonderful thing about looking at questions in the chat. Any parting questions or parting remarks? Yeah.
I do not see any more questions.
Okay. Then I will. So I will make these extra videos. What I will do, my best way to transfer videos to the Living Learning community, I think is still through Microsoft Streams. We'll talk. There will be emails, but I will at least get these posted to the the same place where the other pre-recorded lecture videos are, and then I'll be in chats with the excellent people over at the Living Learning community to figure out where they would like things to be, because we'll figure it out. There are options. We have the technology, believe it or not.
Thank you so much for the revision, Doctor.
Absolutely. Absolutely. Have a good evening, everybody. And we're in person next week. Dun, 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 dun.